Um, Hello everyone, I am Pranoy. I work as a backend engineer at Open Provider. I've been working with Golang for about 6 odd years, and I also do some open source contribution. I have some contribution on Kate, some on Fission, etc. Um, in today's session, we'll see what escape analysis is in Go. What basically we would be seeing is how variables move between stack and heap, right? Yeah, so this is the agenda. We'll first go over some bits of stack and heap. I'm pretty sure everyone here knows what stack is, what heap is, how they function, but we'll still go over it, see the differences to help us understand escape analysis better. Then we'll see what escape analysis is and how to read the compiler outputs. We'll see a few Go tools, few GC flags in order to read compiler outputs. Then certain escape analysis pattern and how does moving between stack and heap affect our GC pressure and performance impacts. Apart from that, we'll then see some of the optimization strategies and then conclude it with a summary. All right, so let's begin. So stack and heap. So everything, your functions, everything that is defined within a scope, your variables within the function, all of those things remain on stack, right? The stack is defined with last in first out memory optimization. It's faster, and everything else that exists outside of a scope of function, something that has to outlive the scope, will go on heap. These are the only two things where your things in your program would lie. But we must ask ourselves a question that does it even matter to our program whether it lives on stack or heap? Now, it does not matter from the correctness of the program. Go will always make sure that it lives in the right place and it makes sure that your program is correct. You don't really have to worry about it. But there are certain cases where you might want to think about where exactly it's living, stack or heap. And that is only in the case where it affects your program, no other ways. Now let's hold this thought because this is something we'll come back to after some time. Now let's just see few differences between stack and heap, which I'm pretty sure again everyone knows, so we'll just breeze through it, right? Stack works with push pop mechanism, last in first out memory optimization, whereas every time you have to store into heap, you need to first do runtime new object, find a location in the heap, find a location in the memory, then also perform bookkeeping operations. So it is comparatively expensive as compared to stack, also takes longer time. Stack is scope bound. Everything that has a life to it might most likely stay on stack, whereas heap, one of the main reasons compiler would want to put something on heap is when it wants to outlive the scope. Stack has little to no GC cost. Function returns, memory is claimed. There is no runtime involved, no pause, no scan, no overhead. Whereas every time a GC, your garbage collector, has to clean something from heap, it would have to pause your program, scan it, and then go ahead and clean it. So it's comparatively costlier operation. Now, if you have a lot of things present on your heap, the more things you have, the more time it would take for the garbage collector to perform its operation. Right. And finally, stack is contiguous. So because it is contiguous, it becomes easier to cache. Heap is not. Heap is fragmented, right? And if in your function you have lots of pointer calling each other, it becomes even more difficult to cache. Great. So I'm pretty sure this everyone knew. Just a recap. Now, coming back to the original point of this talk, what is escape analysis? Escape analysis is a static compiler optimization that analyzes whether a variable can safely be kept on the stack. Escape analysis happens at compile time, not at runtime. If a variable address escapes the function scope, for example, when returning a pointer or stored for later use, the compiler must or might allocate it on the heap. That is basically what escape analysis is. It is the decision that your compiler has to make in order to keep something on stack or heap, and this again happens at compile time. Now, how we as programmers can actually figure out whether it lives on stack or on heap? We can make use of the below flags that I have mentioned here. First is go build -gc flag -m. This is to show us, this will give us the output to describe where exactly the escape is happening. And another flag that you can use is similar one, but it just you go ahead and use -m. This would give you more explanation on why the escape happens. This is something you might want to use when you first start using these tools. Moving ahead, you might not really want to do -m because it becomes slightly more complicated. So, when do you want to use these two tools, right? You would need it if and only if your program is not fast enough and you have benchmarks to prove it. You do not want to unnecessarily go ahead and use those tools every time you write some code. If you have proof that your program is not fast enough, it is not up to the benchmarks, it is not hitting the target it has to, only then you would want to go ahead and use those tools to see where the escape is happening. And if when running those benchmarks, you see loads of heap allocation, only then maybe you want to optimize for it, right? Remember, correctness first and then performance, because unless and until your code is correct, it does its job, there is no point in trying to optimize anything. Cool. Now we will see some of the patterns in which escape analysis happens. One of the most common thing is returning pointers. This is something we do pretty often. Again, this is quite simple, where in the left you see, left, right, this side, yeah. You see a main function, basically calling a new config function, which returns a struct, which returns a pointer to the struct. It's as simple as that. Now let's try to use the tools. Let's try to use the tools that we saw earlier with the -gc -m flags and see what happens, what output it gives us. Right. This is the output that we get out of go build -gc flag -m. Basically, what this is telling us is we have two function calls here, main and new config. It basically tells us that the compiler can inline new config function and main function. What it means by inline is it can put it on stack. And on the third line of the output, where it says on line 4 column 11, which is calling of new config function, that is where the actual inlining happens. So the first two lines tells us that inlining can be performed, which means it can be kept on stack, but only in the next line the actual action to inlining happens. Okay. And the last one is what we are most interested in here, where it says in main.go line number 13, which is this variable, has moved to heap. Okay, cool. Now with this flag, it gives us information that it has moved to heap, but has it really moved to heap at this point? Why exactly it moved to heap? Let's use -m flag and try to see that. Right? It's visible properly, right? Yeah. Cool. Thank you. Yeah. So cool. Once again, when you use -m flags, the output of first three lines look pretty similar. What they are basically telling is it can inline new config, it can inline main. Some additional things that you see with inlining here is cost. So the cost associated here is something a compiler assigns complexity cost every time it has to put something on stack. The default cost is 80, 12 is comparatively very less, 12 and 14. So yeah, and it basically tells us about the function that it has to inline. And in the next line again, it tells us about the actual inlining operation. Cool. Now the next few lines are what we are interested in. Now this is something you once again saw in the previous -m flag also, that the config variable has escaped. Now here it gives us the information how compiler actually figured out why it should escape, right? The first line, the second line here, it says flow of R04 was assigned from %config. Basically R0 is the variable that compiler creates in order to store the pointer address of the config variable. The next line says from %config address of. This is where the address has been created for this config variable. And in the last line it says from return config return. Basically this is where it realizes that okay, now it has to escape because the config variable is going to outlive the scope of the function new config. Another way to read this output is to read it in reverse order. What you would do when reading in reverse order is you would realize that, okay, first the compiler figured out it has to return the config. Because it has to return the config, it needs an address. Because it needs an address, it then needs to store somewhere in order for bookkeeping, in order basically for your program to find that out. This is what happens over here. And finally, the escape happened. So this was a very simple example where we could use these two tools in order to figure that out. Now let's see another example with closures. With closures here, we see that we have a main function calling a makeAdder function, and the makeAdder function in turn calls a closure function. And one thing to notice here is we makeAdder function requests an integer in the form of value. Cool. Now let's do the same thing with this program as well. Let's first try to look at it with -gc flags -m and see what output we get. Again, it's the first few lines, not three specifically. In our case, it's three because we are calling only two functions. But the first few lines always inform us about the possibility of inlining. It says that on line number 7, makeAdder function can be inlined. Then it also mentions that makeAdder.func1, which is a closure function, line number 8, can be inlined, right? Okay, initially the compiler thinks it can be inlined, by the way. It doesn't really think that it might escape. And finally, it tells that it can inline main as well. It will always say it inlines main, but that is something you won't really see in the compiler output. And finally, what it does is it calls the action to inline. Basically, makeAdder function then gets inline at line number 4. And here it says that on line number 4, the function literal does not escape. So here, your functions, your closures, everything is termed as a function literal. When it comes to compiler terms them as function literal. So you would, every time you try to use this flag, use the GC flags, and try to see the escape analysis happening, you would mostly see a function being termed as function literal. Even a closure would be termed as function literal. And finally, you see that on line number 8, the function literal escapes to heap, right? Over here, the function literal, it says escapes to heap. Sure, this is something we saw in the previous example as well, where if something has to outlive the scope of the current function, it would escape. It's similar. But one thing to notice here is, it's not just the function that is escaping. The value of x is also something that our escape closure function has to observe, has to take with it. Now this output does not really talk a lot about it. The -m flag output does not really talk a lot about it. Let's use -m flag and see what the output gives. How exactly we can understand if it has actually escaped. Yes. Okay, a lot of things. Is it visible at the back? Yeah, cool. Thank you. All right. Once again, first few lines can inline with some cost, and the actual call to inlining happening. Great. Now over here, only in the -m flag, we actually get some information about the value, x value, right? It says makeAdder capturing by value. Remember the term, it is capturing by value, right? It is not capturing by reference. Till now, it is clearly mentioning that it is capturing by value always. And then the next thing is what we are most concerned about, which is about function literal being escaped, right? So this is something that this is basically what was skipped in the previous output. What happens here is your x got captured by makeAdder, x is 1, captured by value, not by reference. And then it says function literal escapes to heap in makeAdder on line number 8. What happens on line number 8 is we are basically returning our actual closure function. Now what happens here again is R0 is nothing but your compiler's variable in order to store the address. And you notice it mentions something called storage for function literal. Now it does not just mention function literal because your closure function is not just function. It's the function and also it's a struct containing the function and also its parameters, its values, whatever, right? That's why it clearly mentions that storage for function literal. Now R0 stores that, And in the next line, it understands that the function literal has spelled. Basically, by spelled, it basically means that it has to now outlive the scope. And on line 8, again, it says that function literal has to return. Again, another way to read this is similar what we saw with previous example. You would go in reverse order. You would first say that, okay, it has to return. It realized it has to outlive the scope. Because it has to outlive the scope, it decided to escape. Now, what happens to x? Here, parameter x leaks to storage for function literal, for make adder. This is where it realizes, our compiler also realizes that since x is been captured by our function, closure function, x also needs to be escaped. Even though x has been taken in as value, not as a reference, but because x has to outlive the scope of make adder into the closure, that also has to escape, even though it has been defined as value. One thing you can try out, if you play around, you can maybe use this and try to take x as a reference and see what would happen. It would be something interesting to try out. But yeah, coming back, it says parameter x leaks to storage. Now again, the flow of it tells you clearly storage for function literal is assigned from x, because again, your closure function is a struct. It's a struct of function and its parameters. So your storage for function literal has escaped and basically captured by a closure from x, captured by closure at line number 9. This is where the actual capture happens. And finally, what it tells us is again what we saw in the previous output. So yes, you might want when you start performing escape analysis, there are certain cases where using just -m flag might not be very clear for you. In those cases, you might want to use -m initially to get a clear picture of what works, what does not work, and moving after that, you might not really need it. Some other ways where the escape happens. One such type is interface boxing. This is when Go wraps a value in two parts, right? The first example here is n equals to n is set as 42. In this case, 42 lives on the stack. No heap is involved in this case. But the moment you assign, moment you create a variable v with type interface, basically unknown type, and assign it to value, 42 would escape to heap. Why would that happen? Now in such a scenario, your compiler has to store two different things. First is the type of the variable v, which in this case is an int, and also its value. So it has to store two different boxes, and that is where it has to basically go ahead and escape into the heap. Now in a lot of places this happens very unknowingly, something we tend to overlook a lot. One of them is every time you use fmt println, escape happens because n is boxed. Every time you use errors.new, because error is an interface, escape once again happens over there. And basically you create any variable, anything at all with type interface, basically unknown type, escape happens because boxing happens, interface boxing. Now, is it really bad? Is it really bad interface boxing? Not really. There are a lot of places where you cannot escape interface boxing at all. Doing them a few times once is absolutely fine. It becomes a very expensive thing when you try to do in some complex loops or in a hot path in your code. That is where it actually starts adding on to the cost. That is where it actually starts adding on to the GC pressure. That is some place you need to take care of. And finally, these are some other places where it might escape to heap or might live on stack. Basically, every time you create a slice with unknown size, it might escape to heap. With constant size, might remain on stack. Similarly, you append your slice beyond the capacity, again might escape to heap. Creating maps might escape to heap. One thing to understand here is every time I say something is moving to stack or remaining on heap, I use the word it might escape to heap or it might stay on stack. You cannot just look at the code and play a guessing game that it would remain on stack or go to heap. It's always better to make use of the tools and figure out where it is going. And even when you want to make use of the tools, you only want to make use of it in cases where you actually see some performance issues. You don't want to do it in the blind. Okay, now this is some GC pressure and performance impacts. So I ran the first example, returning pointer from function, and I created just another function to return value. If you look at this, I was using Go 1.25.3, and this is my system that I was running it on. Everything in red is basically the function returning pointer, green is basically the function returning by value. You notice every time we are returning function by making use of returning by pointer, we have some allocation assigned to it. We have one allocs. That is something we saw with our compiler output as well, that there is some allocation. And also the time taken for operation is comparatively huge as compared to returning by value. Now again, if you just look at this, it is not a lot. I mean, you might feel that 12 nanoseconds per operation, it's fine. It might not feel a lot. But if you compare it with the returning by value, it is almost, I think, what, 35 times more as compared to returning by value. So these things add up to your cost. These things add up to your performance. This is something you might want to think of in case you actually see some performance issues and you see a lot of allocations happening within your hot paths, or your complex loops. That is where you might want to start thinking about these things. Now, is it how exactly to figure out what are the different ways in which you can actually solve this escaping? Let's see few examples of how to optimize, right? One way to optimize is try and prefer values over pointers wherever you can. I understand you won't be able to do it in a lot of places. There is a reason we also return a pointer to something. So this is something you have to make a conscious decision about, and this is something you have to decide with certain trade-offs, what really matters to you. Because small structs are also faster to copy than to heap allocate, by the way. So this is a trade-off that you would have to make. But one thing to notice here is that yes, returning values is cheaper than returning pointers. Make use of sync pool for frequently allocated objects. Why? Making use of sync pool will dramatically reduce your GC pressure, especially for short-lived objects. It is one of the main reasons. If you look into net HTTP codebase, you would see it sync pool being extensively used in it. So yeah, there's something to remember. Another one is pre-allocate slices with known capacity. Try to avoid using unknown capacity slices. That would really add. See, every time you extend beyond the capacity, there is a backing array which pretty much lives on heap. That is not something you cannot avoid. But at least try to make the first allocation into the first allocation known and keep it on stack. And of course, it's also better if you can not use backing array and try to figure out some other way, because cost, again, it's a trade-off that you would have to decide to. And finally, inline small structs. This is some very small optimization that we did. Earlier, in our registry structure, we basically returned pointer to connection and pointer to config, which we turned in and used instead of, we started using embedding instead of pointing. This helped us with fewer dereferences and better caching, comparatively less GC cost. Yeah, these are some of the ways in which you can optimize. But again, like I'm saying that again and again, this is a trade-off that you would always have to make. If only and only if you see performance impact, only then you want to do all of this, figure out and see where you want to optimize it. And even when it comes to optimization, you want to optimize only in places that are concerned with your hot paths, basically in a piece of code that has been called again and again, or within your for loops. You don't want to go ahead and optimize everything, right? And finally, going back to the summary of what we saw in this talk, escape analysis is compile time. It does not happen at runtime. Compiler decides while compiling itself whether it should stay on stack or on heap. There is no runtime overhead and for the decision itself. Next, not all heap allocations are bad. Remember, premature optimization is the root of all evil. Profile first, have your benchmarks, have your test cases, have a target. And only if you see your performance is not up to the target, your profiling is not up to the target, that is when you want to actually go ahead and do escape analysis, think about optimizing. Otherwise, it's fine. Leave it as is. Your program is fine. Go make sure it is correct always. Interfaces and closures can be a huge culprit because interfaces, unknowingly, a lot of times they escape. We don't really realize that boxing is happening, interface boxing is happening, and we end up using that a lot. So try to prefer concrete types, pass state explicitly, avoid FMT functions in tight loops if you can. Yeah. And yeah, sync pool is a really good friend at scale because it amortizes location cost across Go routines. It is used throughout the Go package. You can start, if you actually want to see how it has been used, you can actually explore net-HTTP package in order to understand how Go uses it in its program as well. So, and Go actually probably uses this for exact same reason, to reduce the GC pressure. Yeah, that's it from me. Thank you. I'm Pranoy, and this is my LinkedIn in case people want to connect. Yeah.